well, humans write that, but it's a computer doing the work and not us. Humans write stupid, recursive, repetitive code. It turns out that that's the kind of code compressors like. The sophisticated code that a C compiler turns out doesn't compress as well as a human's code. So just by writing it in assembly language, you get some pretty good savings without trying very hard. And if you do try hard, you can get even better savings. For example, if you explicitly use the same registers for the same tasks over and over again, the compressor learns about those patterns and just repeats them. I did it, and we got an 114 byte reduction. Not much, but if you're willing to try it, you can get some good savings over a sustained period of time, maybe enough to fit in another effect or two. That's about as far as it's going to go. Let's start adding some stuff back in. We've got over 3 kilobytes to work with. Let's add some music first. I'll talk about the music, and then Polaris will come back and he'll talk about some graphics. Now, your first reaction might be, if you've ever written a demo before, oh yeah, we'll use an MP3 file, get our musician to make some music for us, we'll get some artists to do some JPEG textures for us, we'll get some objects using a 3D modeler. Well, that won't work, right? Because JPEG's probably going to be 20K, your MP3 is going to be like 2 megabytes, and your 3D objects, I don't know how big those are going to be, depends on the complexity, but probably a couple 100K. So even with the best compressors, you're not going to be able to do it. Instead, what you're going to have to do is generate everything that you see in your demo using algorithms and code. So you'll find fractal algorithms online for generating textures that look nice. Use those instead of storing the same texture as a JPEG. All right, so when we start talking about audio output, we have to talk about how we're going to get the audio out to the speakers, assuming we know how to generate it. The typical way you do it in a 4K intro, because you're cheap and you don't want to spend a lot of space, is to do buffered audio. Basically, you create a big buffer that's enough space to hold 2 minutes of audio or whatever your demo's length is. You write all your music into the buffer before your demo even starts, and then you play the buffer back using something like PlaySound as a WAV file. Then the operating system's playing the sound, and then you start doing your graphics. The easiest way is using the wave out write function. There's also PlaySound, which is somewhat unreliable. And then there's direct sound, which can get very sophisticated with effects. So like you can get free reverberation effects using direct sound. But it's also a little bit more space consuming and harder to use. All right, the basis of any audio output routine is going to be something called an oscillator. Basically what it does is it generates a continuous waveform. The simplest one probably everybody knows about is the sine wave. So here we have a loop. It renders 16,000 samples. Each sample, we add a frequency to a counter, so this variable is constantly going upwards. And then we take the sine of that variable, the sine function, and then we add that into our audio buffer. And that creates a sine wave that sounds something like this. That sounds boring, and it's not very good, but you can experiment with other wave shapes, triangle waves, sawtooth waves, square waves, clipped triangle waves, all sorts of shapes. Another approach you could take is something called FM synthesis, where you use one sine wave to alter the frequency of another. So, for example, you can create bell and drum sounds using this technique. Here I have the same counter plus frequency, so this variable is always going up. Take the sine of that, that makes an oscillator. And then the second oscillator down here, it's the same thing, except that the frequency is being adjusted using the first oscillator. So you can get some very interesting wave sounds with this. That sounds kind of like a bell, roughly. Now, if you really want high-quality audio, the Windows operating system contains a file called gm.dls. And what you can do, open this file. It contains wave samples of various real instruments. So you simply load those samples up and play those back as your oscillator source. So you get high-quality sounds of real instruments instead of doing some cheap sine waves or something.
And I'll mention one other thing in there. This is the modern-day equivalent of those ancient, no, I shouldn't say ancient, older programs that was when I was originally first starting in the demo scene that would actually take advantage of the sound card's wave font data inside the card itself. So it would go to the sound card, said, give me the sound of a drum pack, give me the sound of this or that, and then it would mix it together in order to create a new wave. This is the same idea, but just done X amount of years later.
Although some people consider this cheating because you're using someone else's waveforms and not yourself. But hey, it's built into the operating system. It's not against the rules. So, all right. The next step, wherever you get your oscillators from, whether you do them yourself or you get them from gm.dls, is to do envelopes over them. Now, real sounds, they don't just cut in, play, and then cut off. A real instrument sound, you hit the string or you hit the drum. It comes in from silent up to loud rather slowly, and then it tends to decay over time, so it gets quieter with time. So in order to get good instrument sounds, you have to apply this sort of an amplitude envelope to the sound itself. So for example, here we have an oscillator. We multiply it with this envelope function before we write it out to the buffer. And the envelope function implements this sort of curve that generates a nice pattern. So if we do this to our bell sound, this is what we get. You can see that it has a very pleasant sort of beginning and an end every time it hits, as opposed to just sort of clicking on and then clicking off and just being silent. All right, now we've got some sort of sounds, not very good sounds, but they're sounds. Now we got to somehow play them back. We have to have a sequence of music, right? Musical score, notes written down somewhere, and then play those notes back. Typically what you'll do is you'll have a block of memory that contains your note data, and then you'll have some sort of loop that every time it sees a note, it writes it out to the buffer. Or you can hard code it like I did in this example. Normally you would never do it this way. One demo we did do, the Ethereum, was written this way. It worked, but our musician was pretty hardcore to be actually writing his music in C. Most musicians don't like that. All right. So that pretty much covers the basics of a synthesizer, a software synthesizer. This is about the most primitive you can get without sounding like crap. But the good news is you can make it much better. For example, you can use filters to increase certain frequencies or decrease other frequencies. You can use reverb and delay to add some sort of depth effects. There are many more. There's like compressors and equalization and all sorts of things. You can also give musicians more control, like because you're a coder, you probably don't have very good musical skills. Maybe you do, I don't know, but typically that's not the case. So musicians should be able to adjust basic things like the length of the note, the volume of the individual notes. Like the other sample didn't really address that. They should also be able to adjust like instrument parameters, like how much reverb we have, what frequency cutoffs we have, things of that nature. And another thing you can do to improve it is instead of rendering it all to one big buffer, which takes like 10 seconds of loading time before the demo starts, you can go ahead and render sample chunks and then play those chunks back in real time. But that takes more space, but I mean, on the other hand, it makes it somewhat nicer, so that's a trade-off. All right, this next part is up to Polaris, and he'll talk about object generation real quickly.
Okay, thank you.
That's my microphone.
So actually, it did remind me of how Amdesh 4 did that music. Well, he wrote it all in C. I spent August long weekend writing it all in assembly and having him debug over the lake with his cellular phone saying, it doesn't sound quite right. I think you've got the assembly wrong. So that was a fun time. But again, just as Estek mentioned, you need to move from thinking about digital assets to algorithms. And this wireframe sphere model, which is a bunch of clods, has 4,800 vertices. We're talking about a program that has 4,096 bytes. A vertice is typically a tuple of 3 x, y, and z coordinates in which you may have floats representing them. So you have 32-bit numbers, right? So if you do that, you end up with the raw model being 56 kilobytes, right? We're trying to have something in 4 kilobytes. So obviously you can't store the raw model. And if you're talking about using UV texturing, which is just a fancy way of saying having coordinates for putting a texture around the sphere, that balloons again up to 93 kilobytes roughly. So again, not possible. This texture here, which is a very basic texture, is 256 by 256. It's 24 bits, basically red, green, and blue, so 3 bytes, and its raw format is 192 bytes. So obviously storage is not an option, and we need to use algorithms. So this is a part of a texture generation algorithm that basically says, hey, if I'm sort of in this Y section, this X section, this Y section, this X section, it's basically testing to see if it's in one of these sections. And because this is 256 by 256, 128 or 128 is the middle line. And so we can see we're testing against the 128s. And it says, I'm going to make that white. So 255, 255, 255. And this code, albeit very simple, okay, it's extremely simple code. It is easily compressed, and it works out to be 160 bytes. So we can actually have a little program that, inside an executable that takes 160 bytes to create that bitmap. It's also possible to do tessellation algorithms, which basically is a fancy way of saying making triangles or composing an object out of triangles with the 3D API. So here I have basically this being represented. I'm drawing the sphere now, creating all of those using some basic trigonometry. And that code, the very first part, rotates quads on an x-axis, and then it rotates it on the y-axis. So what happens is it draws each segment top to down. So it's going from zenith to nadir, so at the top all the way down. So I wrote that code, put some UV coordinates on it to create a bouncing ball of sorts. However, one of the most fundamental things you can't forget about, remember GMDLS, making use of the operating system? Well, again, know your environment, know your turf. So I wrote that code and it took 280 bytes. Sounds pretty good, right? Well, OpenGL has a code that basically is called, glue sphere. Make me a sphere. So all of a sudden, making use of that, it shrinks down to 145 bytes. So know your environment. And I wasn't trying to make the best sphere algorithm in the world, but the advantage of calling a library is that you only need the code to call the library. You do not need to have the code of the library. So with object generation, OpenGL and DirectX or D3DX have a number of primitives. So you have cylinders. You can think of those as tubes, cubes. Those can become buildings. You have spheres. Those can become planets, right? Disks, Pac-Man, etc. Teapot. I'm waiting to see a 4K with a teapot on it because to make a teapot in D3D, it actually has a teapot model, which is sort of a tip of the hat to the Utah teapot, which is a famous 3D model. But know where to use your algorithms and when to use the local system. Supershapes. There was a famous production called San Angeles Observation, thank you, which used supershapes. And this is an area where you may wish to use some algorithms. You can see you can create beautiful things with algorithms to describe objects. And you can think of them like, starfish, right? Spaceship. Crazy bowling ball. Something that I dreamt last night and scared me because it was 4,097 bytes. So you combine all this together, and we have a miniature 4 kilobyte example. Our production takes roughly 1,426 bytes, and I've tiled the texture using a matrix, again, leveraging the code environment. So you can see we've got this little example. Maybe we'll do that again. What the heck? There we go. Right? Yeah. Now, one of the things which I will mention is like, okay, well, that's maybe a quarter of the size we've got to play with, maybe closer to a third, somewhere between a quarter and a third. Remember, whenever you're seeing it, there is this critical mass of what it takes to put a production on the screen. Initializing the window somehow, right? No matter how sneaky it is, it still costs, right? Creating interfaces to the D3D or OpenGL interface, right? Doing all of those things has a bit of a critical mass.
I think Crinkler's base size, if you have a 0-byte executable, is like 500 bytes just for Crinkler.
Exactly. So with that, it means that there's so much more you can do beyond it, but you've basically got, at the end of the day, you've got a lot of space to play with.